You can look at a picture, you can imagine a picture, you can attend a picture, you can detect a picture. The same cortical machinery is being used in every one of these cases. So this is an example, I think, where developments in AI have been essential. There's something wonderfully satisfying about mastering a hard thing that you know can be done and doing it super well. And it's tempting to trade that in for the uncertainty that you live with all the time when you're trying to figure out your little slice of the question, how does the brain work?
This is Brain Inspired.
Is there a difference between seeing a tree and imagining a tree? If so, what is that difference? And what does it say about how our brains process and/or imagine images in our heads? Today, my guest is Thomas Naselaris, who knows a bit about that. Thomas runs his lab at Medical University of South Carolina, where if you go, he may put you in an fMRI scanner and show you a famous painting, then later tell you to just imagine that painting. And when you're all done, he'll use encoding and decoding models to predict how your brain responded and what information was in your brain. We talk about all of that, as well as how far along we've come with fMRI in general and how much farther there is still to go. Thomas is a co-founder, along with Kendrick Kay, of the Cognitive Computational Neuroscience Conference, where folks studying biological intelligence and artificial intelligence come together to share ideas and good times. So with regard to the CCN conference and otherwise, we talk about the current state and outlook for how the AI and neuroscience worlds are and are not interfacing well. And Thomas also describes this huge fMRI dataset that he and Kendrick Kay have collected, from which they're starting to be able to infer entire visual system network models. You can visit his lab website to learn more. That is at naselarislab.net, or go to the show notes at braininspired.co/podcast/55. Carson, Alexander, Chad, Thomas, Jeff, and Lisa, thank you guys for your support on Patreon. I will be sending videos from the Brain Inspired course your way in the coming weeks. If you're a new listener, you can learn more about that at braininspired.co/course. The mountain in my backyard just opened for ski season, so I am strapping on my snowboard and heading there soon. Somewhere deep in my visual cortex, months ago, I clamped a representation of that snowy mountain, and it's been blurrily infiltrating my early visual cortex ever since, but now I get to pass it through my retinas as well. I hope that'll make more sense to you after you enjoy Thomas Naselaris. Thomas, thanks for being here and welcome.
Thanks for having me. It's fun to be here.
What in God's name made you quit the glorious gold standard world of monkey neurophysiology and go into human fMRI? And were you ridiculed for doing so?
That's a good opening question. A lot of reasons. I think, some of them were circumstantial. I ended up in a lab that was, I think, just on getting started, developing a really, I think, interesting and intriguing approach to fMRI. And I had the opportunity to work with people in that lab. This is the Gallant Lab at UC Berkeley. Mm-hmm. The people being like Kendrick Kay is still a good friend and collaborator.
Yep.
So that, that was circumstantial. If that hadn't been going on in the lab at the time that I got there, I probably would not have made the transition. But why did this set of circumstances, why were they compelling and interesting? So I came from, as a graduate student, I came from the lab of Georgopoulos, Apostolos Georgopoulos, who was studying population activity.
Yep.
So the idea was to record as many neurons as you could and build models that helped you understand how whole populations of neurons were coordinating, in this case, arm movement. Very simple behavior. And I thought it would be interesting to try to take this population approach to vision. So my initial idea going to Jack's lab was that we were going to record for many neurons in the visual system and try to build transforms between stimulus and brain activity. So transform, going from stimulus to brain activity is what's called an encoding model. And one of the things I was particularly interested in was reversing the transform. So taking population activity and constructing a picture from that. That seemed like an interesting and cool thing to do at the time. It still does to some extent. And I mean, to get that to work, you need lots of neurons. And while I was, busy kind of setting up the techniques that we would need to move from the single cell recording paradigm that was going on in the lab at the time to multi-neuron paradigm, Kendrick came by one day and said, "Hey," well, I don't know what he actually said. I'll just confabulate. Something like, "Hey, let's just do this with fMRI. We have the whole brain, every part of the visual system, right? You'll work for 2 years to get 500 neurons, and I can give you 5,000 voxels tomorrow."
It's data.
Yeah, right. So the question was, were the models that we were intending to build, the encoding and decoding models that would map stimuli to and from, in scare quotes, real brain activity, would they work when the activity in question was this kind of weird aggregate signal coming out of a voxel that took, a million neurons, probably averaged them in some way, and then ran them through this nonlinear plumbing operation. And it was just totally unclear that any of the insights we gained from decades of cat and monkey physiology would apply. Now it seems naive to be surprised by the fact, but they did.
Yeah.
And it very quickly became apparent to me that no analysis that I was even considering throwing at neurons would fail when I threw them at voxels. So now I have the entire human brain, multiple processing levels, many quasi-independent units, and a connection to the computational work, or a contiguity with the computational work that I wanted to do and that had been ongoing in physiology. Now add to that the fact that humans they're just a lot more pleasant to work with than what I was working with before. They don't.
Yes.
Most of them are. Most of them are. I mean, there's no comparison. But if what you want to do, like what I wanted to do, was play with data.
Yeah. And
I was willing, and I had built up a skill set, a surgical and veterinary skill set over the years, in order to give me access to the data I wanted to play with. And all of a sudden I
drop that.
I was surprising. Yeah. So I didn't drop it immediately. I remained part of the physiology project until the end in terms of Jack Gallman's lab. I mean, I think I implanted one of the last Utah arrays that they used. I think maybe they can correct you.
The whole surgical suite of skills that you learn is that's interesting because it's basically useless now. But if I'm in a room, I've had this thought occasionally, it just kind of pops up if I'm reminiscing, like if someone fell and, their skull busted it open or something, I am most likely the best person to attend to them in that situation, which is a crazy thought.
Yeah, you could probably do, slightly less harm than good, I think.
Yeah, less harm.
Yeah.
But did anyone tell you, hey, you're going down the wrong path here, you need to stick with monkey neurophysiology?
No. I mean, the Gallup lab was at least at the time kind of insular. We were all sort of feverishly working on our own little thing.
Yeah.
And I was getting positive reinforcement from within the lab. And things started working well really quickly, and we were getting positive feedback in the form of publications. So it didn't, no one said, what the hell are you doing? In retrospect, there's a problem with making that transition, just in the sense that, while people who started doing fMRI as grad students and continued to do it through their careers, where they were learning the kind of art, the arcana that goes with any imaging modality. I was learning a completely different set of, voodoo magic spells. And so that, I didn't really appreciate the extent to which there would be a kind of learning curve. When I started my own lab, I was like, I'm an fMRI researcher now, and I have to build this infrastructure in my own lab.
Oh, yeah.
That actually took some doing. But that's whatever. Anytime you try something new, you have to deal with that, so it's fine.
I have an EEG friend who just, a couple of years ago started his own EEG lab, and it seems like that took much less. It was a much faster learning curve. I mean, he had done it in the past, so he knew what went into making a rig and everything. But it's a less of a beast, I think. I mean, it has its own issues as well. So.
Yeah, I mean, every measurement modality is its own specialized craft.
Well, and starting a monkey lab as well I was always worried about that. Like, oh my God, it takes so much to just in administrative issues alone.
Absolutely, yeah, the whole administrative aspect of it, and so it's heroic work, and so I am convinced that fMRI is essential. It's an essential tool. So I described to you sort of why I was able to make or how I rationalized the transition at the time. I still think there are good reasons, but my appreciation for fMRI has grown immensely because when I started my own lab, I started studying things that really only humans can do, that's too strong a statement. That is very, very difficult to study in non-humans. And that's mental imagery. It's a relatively easy experiment, or at least set of instructions to tell a subject, close your eyes or whatever, stare at a blank screen and imagine a unicorn. And you could develop some kind of animal model of that, I'm sure. Probably people are working on it. But one of the defining aspects of mental imagery is the subjective phenomenal component that subjects can communicate and confirm took place. They can say, yes, I did what you asked me. In fact, you can be the subject in your own fMRI experiment and confirm to yourself that you imagined things you were supposed to imagine. So that's a really, I think, important thing, right? And mental imagery is just one of the phenomena that are so much easier to access, or maybe only, it's only possible to access if you're working with humans. I mean, language is the other obvious phenomenon. But, the kind of cognitive flexibility that humans show, you can just kind of give someone a set of instructions, a set of visual puzzles, and just tell them to solve it, and they just will. So being able to access the processing that takes place when uniquely, or let's say strongly human cognition is going on, I think it's essential. And I think fMRI is unparalleled, and it's in the access it gives you to that.
Well, you just ran through multiple topics that we'll dive a little deeper into here.
Okay.
I want to back up and kind of ease our way into it. One of the things I was going to ask you, speaking of head injuries, is were you a skater growing up? But now I know you have skateboards on your wall behind you as we're speaking, like frames.
I remain a skater.
You're a skater.
I am. There's a skate park about 5 minutes from my house here in Charleston.
Wow.
With two lovely bowls and a snake run and a street course.
Were you a punk kid?
No. I think I didn't really embrace skating culture.
Oh.
I mean, I had no problem with it, but that kind of punk aspect of it, I never really got into. I think I like to geek out on the technical aspects of skating when I was young.
Gotcha.
Now that I'm old and I'm slow, I like just carving bowls, dropping in, and just doing like, there's such a division at the skate park between dudes who, you know, like the 45-year-old dads and these, you know, 7 to 16-year-old kids.
You're not trying to keep up with the lingo?
No, that would be absurd. Preposterous. I mean, you know,
you draw the line somewhere, for God's sake.
Yeah, I don't even try. I just kind of keep my distance and watch and admire these kids. The insane, beautiful, insane acrobatics that they pull off feet away from me.
It's too bad you can't skateboard in an fMRI rig.
That would be a challenge to break down and study. Yeah.
Well, imagination, I suppose. Imagery, skateboard imagery.
Yeah, you could.
Okay. So, Thomas, I get listener emails asking for advice here. And in one, the emailer was seeking advice on how to achieve this very particular state in terms of their career, like the trajectory. They had a very particular trajectory in mind that they would end up studying this very particular thing in this very particular way, using these very particular methods. And part of my advice was to not worry too much about the destination, because the minute you learn something, you discover how little you know, and your path and your goals change. And that happens about once every 2 weeks or so until you die. I also advised to eat healthy and try not to die. But so
good.
Was that good advice or bad advice?
I think that's perfect advice. I would add, though, you said that's something that happens every 2 weeks. I would say that happening 2 weeks, an exciting vista of confusion that pulls you in multiple directions and makes you uncertain about which way you're supposed to go. That happens every 2 weeks if you're doing your job. You know, if you're constantly pushing and challenging yourself and casting yourself into, you know, new questions, new terrains. That's the excitement, the exhilaration, and the exhaustion of science. The
exhaustion. So in some sense, it's not a punishment, because it's a punishment and a reward for doing your job well, I suppose.
Yeah. You know, I've spent a lot of time in the past thinking and talking to other people about what the right metaphor is for science. You know, and because sometimes it's kind of like, it is like you describe, it's hard, but you feel like you're ascending to some new vista, and, you know, a vista with like an infinite horizon, and all will be revealed to you.
Yes.
You just make it up another few feet.
It's a false summit.
Of course, right, it is. And you keep climbing and climbing, but you do get higher and higher views. It feels like that sometimes. I think other times it feels like you are toiling to like dig a grave for your best ideas, you know, like where your best ideas will be buried.
Well, that's the thing. It's like you're working so hard, and it's the harder you work, it's like the bigger shovel full of dirt that you're scooping out for the faster you're digging your grave. So that's a real conundrum.
Yeah. I think lots of metaphors apply.
Well, thanks for talking with me today, Thomas. It's been a great conversation. let's not end on that, I suppose.
Okay. No, that's a little grim.
Is there some advice that sticks out in your head that anyone has given you that you might consider the worst advice you've ever gotten in terms of science?
Oh, no. I think to the credit of many of the mentors I met along the way, many of them sort of delivered, not to me individually, but to sort of my cohort, these prognoses about like what our likely fate was in science. You know, and we had one of these, you know, classic talks in my first week of grad school, where this professor, very successful, you know, and just kind of hard-edged kind of dude, was like, 80% of you will not have the job that you think you're going to get.
God, yeah.
Right. So had I interpreted that as advice to do something else, it would have been bad advice. But I don't think he was delivering it like that. He was just saying, these are the stats.
Yeah, he wasn't saying go away.
No. So yeah, I honestly I can't think of any advice I've received that's had much impact one way or the other. To be honest, I mean, because again, there is so much uncertainty in science.
Yeah.
You never really know if the thing you're working on is going to yield. It's going to yield what you hope it will, or if it's going to lead to just another problem or a dead end. And you can ask people, is this the right thing? Am I doing the right thing? And there's so much noise in the feedback
So
you
much
get.
noise.
It's like the review process. So nothing really stands out as particularly bad.
How important is it to sort of stay the course in what you're doing as you're toiling away at something and you don't know if it's going to work out, and it seems like it might not, but you have this gut intuition. What's the right amount of intuition to stick with versus amount of clarity received from facts?
Yeah.
We'll move on soon.
I feel like if someone had kind of said what you just said in an assertive way to me, that would have counted as good advice. So allow me to offer advice. And that is, perseverance is essential. And any scientist will tell you this. Most breakthroughs come long after you kind of are the original excitement of the idea that motivated you to get into a project has kind of decayed into, and has transformed itself through a variety of different emotions, like dread and determination, and then re-excitement, and then re-dread.
Failure acceptance.
Yeah, right. So you have to commit to multiple cycles of attempt and failure, false discoveries and things like that, until you kind of ground out in something that you're convinced is probably pretty true. And just pushing through, keep continuing to push, especially if your own like personal velocity is slow. I mean, which I think is fair to say about me. It takes me a long time to bring projects to completion usually. So I think it's particularly important to keep going.
Well, that is another frustrating thing. I know we're talking a lot of culture here, but you have this idea and you can sort of immediately see the project and how it's going to turn out, how to set it up, how to implement it. But you don't realize the end, that what you're seeing is actually 20, 30 years in the future.
Could be. Yeah.
It's really disappointing.
And its resemblance, this mental image you have of this thing that the project is going to be, it often is really poor approximation to what you end up with. But so my wife is a clothing designer, and we talk a lot about the creative process. I think it's really the same in science as it is.
I believe you. Yeah.
In the arts, you kind of get this idea about the way things could be, and so you're creating a narrative or maybe a picture, and then you go, and the process of checking if that's true is very similar to the process of putting an idea on paper or into words. I think for an artist or a writer, like the immediate feedback you get is, it always causes you to refine the initial idea.
It makes one hesitate to proceed because as soon as I do something that's worth doing, that's any sort of progress, the feedback is going to be rough.
Yeah.
Make it hard. The resistance is hard.
To make an idea, ideas are another metaphor, science as parenthood, or at least midwifery, right?
Yeah. Oh,
like,
God.
So you're bringing an idea out into the world. It is at once the most precious and most vulnerable thing in the, a new idea. It's like a baby. There's nothing more precious, nothing more vulnerable. And it's immediately going to get exposed to all kinds of abuse, and the world is not going to accommodate it. I mean, the world does not accommodate your theories in the way that you want it to ever, And so that's another helpful way of thinking about the scientific process, I think.
Don't have kids, guys. Don't have kids. So you ran the show at Cognitive Computational Neuroscience Conference this year. Your friend and collaborator, Kendrick Kay, with whom you conceived this idea and decided to execute on it and have executed well. So I know Kendrick is kind of lazy, I guess, right? Because he didn't even attend this year.
No, that's not a word I'd use to describe him. I think he maybe oversubscribed. I mean, he's got a lot of projects. I'm one of his many collaborators. He's doing lots of things at any one time. Yeah, so I think that, and he and I have multiple projects together, and we sort of trade. We can kind of have a sort of an economy where it's like I'll work on this and you work on that. So I totally understood his choice this year.
It was my first time having currywurst in Berlin this year, which I thought was okay. Currywurst is okay.
We're achieving our mission of cultural exposure. Or something.
I did. I took that home, and the other thing I took home, besides things from the conference, of course, but culturally, right. The other thing I took home was, good God, they smoke a lot there. I couldn't believe it. Yeah,
it's almost like the effects of smoking are just like this cultural thing. If you smoke in the right culture, you won't get cancer.
Must be. Have you recovered? You did a great job. It was really impressive to see you keep your head on straight and organize the whole thing and just keep it running. So have you recovered from the experience yet?
Yeah, I think so. I think I'm like everyone else. Like what you really want to be doing is just being in your lab, working on your projects and ideas, stuff like that. So when I got back from CCN, I immediately just kind of put it out of my mind and started working on stuff that I was excited about because, of course, I got all kinds of ideas and inspiration from the conference itself. And now I think so it's been about a month or two, and now I'm kind of getting back to organizing 2020 and grant reviews and submissions and
woohoo
papers. The whole
The whole rigmarole. I'm out. See, things. I'm out of it. I opted out.
You're kind of, this is the good stuff. You're focusing on that.
So the kind of the point of CCN is to bring together these diverse fields: neuroscience, computational neuroscience, artificial intelligence, cognitive science. And as you gain more experience, what do you see as the ongoing challenges to bring these fields together? Are there things that you've learned throughout? Kind of each conference, each iteration, like, do you see a pattern of ongoing challenges?
So, some of the challenges are very generic, and the things I've learned, some of the things I've learned are very generic, just about human behavior and coordinating lots of humans around it. But that's not your question. So, there's lots of things. So there are cultural differences between the different disciplines that affect, for example, expectations around publishing. AI is, as a field, people build their reputations to a large extent publishing and conference proceedings. And those are, in some sense, not considered a real thing in biology, in neuroscience.
Fast and loose, kind of considered.
Right.
Yeah.
Right. It's a weird thing. So the submissions to a conference are much more rigorous for engineers and AI people than they are for many neuroscientists, where you might just submit an abstract and it's sort of some quality control is applied. But then the paper process of, getting a paper through review is extremely rigorous in biology.
Yeah.
It can take a year from the time you submit a paper, which is, for a conference proceeding, unheard of. So there's that kind of stuff. But I think obviously though the conceptual issues are perhaps deeper, or at least more interesting. So one of the things that's come up, and there's a sort of asymmetry between neuroscience and AI right now. I think not everyone feels this way, but there's a sense in which AI is making a lot of progress by sort of operationalizing concepps that are loosely sort of related or borrowed, maybe.
Well, they use the same term.
Psychology. Yeah, they at least use the same language, and they use some of the concepts that are in neuroscience. But it seems like the cycle between AI and neuroscience felt tighter in the past, whereas now the things that can be done in terms of building really impressive systems that can accomplish tasks that many neuroscientists wouldn't think to study in the laboratory. They're so complex. And I think it's actually at the level of task that there's a real...
Like what? Do you have an example?
A real distance. Like driving a car.
Oh, yeah, sure.
Or just like captioning an image. right?
Yep.
I mean, just having someone look at 100 images and write out a caption, right? And just scan their brain while they're doing that. Okay, now go. Tell me what happened. And neuroscientists tend not to do experiments like that.
It's such a more straightforward, it's application based more than understanding based, it seems.
Right. So there's another, I think, shock or surprise to me that a relatively small set of tools in this kind of deep learning age can be utilized to solve tasks that I would have thought would have required much more sophisticated ideas and machinery to carry out. Now, you could argue about the extent to which AI people are really solving the really hard tasks. I mean, captioning is a good example. I don't know. I have to be careful. You have to be careful whenever you say what AI can and can't do. Because next week's crop of papers will belie what you said. But last I checked in, the kind of rich interpretive interaction that human beings can have with a painting, for example, there's nothing like that in AI, right?
But the caption might come out the same.
Wait, what do you mean the same between the?
Well,
AI
if I'm looking at the Mona Lisa, what an AI caption underneath a picture of the Mona Lisa might say, whatever my internal milieu of my experience looking at the Mona Lisa, the caption, the text might come out the same as an AI's would, right?
It could. But as a neuroscientist, I'm very happy to just immediately move the goalposts, and we move them weekly, apparently.
Yes.
Right. So okay, like give me an AI system that can tell you, is her smile menacing or altruistic? What is she smiling about?
When you finish that sentence, you hear boop, 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 and then they come back a week later with something that can do that, right?
So you put your finger on the disorienting pace of AI research relative to neuroscience research, right? So I mean, one of the things I was doing for a while, and I still am to some extent, is taking AI systems and kind of opening them up, and they give you a bunch of states and variables, and you can regress them onto the brain. And that the whole craft of regressing big complicated models, the guts of like big complicated models, onto lots and lots of different parts of brain, that in and of itself is a piece of work that you can put a lot of work into. But the interesting part is the model, right? The one that supplies predictors.
Mm-hmm.
And that project right now, or that way of approaching or kind of linking AI and neuroscience, I think is really hard to do, simply because the space of models that could be compared is overwhelming. It outstrips what anyone can do in a laboratory.
Yeah.
And the complexity of the models, and the rate at which they're being developed. So I almost see. I'm still thinking this through. I'm still processing. I mean, it's because I think right now it's anyone's guess what the relationship of neuroscience and AI is going to be.
See, that's your problem. You're a processor. You're a slow neuroscientist. You need to go in the AI, the fast cycle route, man.
Yeah, I don't know how that's doable. I just
stop thinking about it and just do it. Damn it.
Yeah. Sure. That's good advice. There you go. Yeah. So I mean, I guess this kind of confusion, these asymmetries between AI and neuroscience in terms of their pace, this kind of quandary that neuroscientists are in. What do we do with all this computation that's been going on, and that seems to be solving hard problems, hard tasks? We would love to have an explanation for how the brain does any one of the tasks that a lot of these AI systems are solving. I just think the uncertainty around those questions is motivation itself for the conference. You could take the stance that if you're doing AI right now is a good time to just do it and not necessarily worry about whether some new operation I've coded up is taking place in the basal ganglia, or is it, prefrontal cortex? But my prediction is that the kind of techniques that are driving progress right now will plateau, as they always do. The goalposts for explaining human behavior, creativity, intelligence will seem just as distant as they've always seemed. And the intuitions and insights that neuroscientists produce on their yearly instead of weekly basis or rate will be essential. That's my operating assumption.
Well, you have to have that assumption to stay in your field, to keep doing what you're doing, right?
You do.
Yeah.
You do. Yeah.
For the conference in particular, are there, and in this past one, for instance, were there topics that you thought were underrepresented or missing, or, what are areas with, just from your vantage point, with maybe the most opportunity for someone to enter the field and make viable progress, advance the field?
Okay, so one thing that was missing, and this is something we can work on, is I think motor control and its interface with robotics.
That's interesting that that's missing. You wouldn't expect it.
Yeah, well, it's something I personally would like to learn a lot more about. Especially, just again, personally, I started out doing motor control and thinking a lot about that. Yeah, so I would love to see more of that work represented at CCN. But it sounds like there's, a place to jump in and make progress. Is that what you said?
Well, that would be a place. But the motor push is interesting because I think that is a wave that, I thought that it was sort of on the upswing. I know perception, of course, has been there, and it continues to be massively represented in the literature and in people's labs. But the motor function as an important cognitive function is on the rise, I feel, as a thing that brains fundamentally do. That's a strange thing to say. Like, what brains are computationally for? The answer, movement, seems to be on the rise.
Yes. That idea, I feel like I'm running into it more often. Intuitively, it's really appealing. All the sensory processing it has to be set up in a way that makes the coordination of movement efficient and meaningful. What I don't know right now is the extent to which, techniques that are being used to solve computer vision problems, which is the branch of AI I'm most familiar with right now, how they're faring in terms of solving control problems. I don't know the answer to that. It's something I've, been meaning to learn more about. It seems essential. Yeah.
That's the one thing that you don't know about right now. I like that. Yeah. Not you. My words, not yours. What? So just a couple more questions about this sort of stuff, and then I want to get into what you do and your approach in doing it. What do you think if you had to choose, if all your skills were gone, what would be the one skill that you would try to tackle going into this broad sort of neuroscience AI field?
All my skills are gone. Or you mean like if I was starting over?
Yeah, you're a skater, you're on the half pipe, and you're like, hey, I think I want to get into neuro AI, but I don't know, what should I learn first? And, what's the most important thing for me to know?
Math.
There it is, folks.
To get a math major. I think it's the most all-purpose. It gives you a technical skill, and it's an intellectual workout. But that's funny. Because I started off as an undergrad, just kind of a humanities.
You were math and philosophy, right?
Yeah, but I started off just taking literature classes and
worthless.
And philosophy. Priceless, I would say.
Priceless, yeah.
Yeah.
All right.
And at some point, realized about most of the things I was interested in philosophy, you could actually, you're kind of lucky enough to be born in an age where you can attack them scientifically or address them scientifically. And I realized this passion, this interest, this opportunity rather late. I was like a junior.
Undergraduate?
Yeah. I had spent, 3 years just doing soft science at best.
Tolstoy or Dostoevsky?
Back then it was Dostoevsky. Now it's Tolstoy for sure.
Me too. What the hell happens to us as we age? All right, that's a different question. But
that is,
Well, okay. So what do you think is like the least? So math is the most important. So what do you think is something that you consider a waste of your time looking back? You think that the literature was priceless, right? So what's least important, or what was a waste of your time, you think?
Nothing. I've gone down a lot of dead ends, obviously, like most people have. But I've always learned learned from them. I guess I could say it might have been better for me to have started studying science a little bit earlier, but I don't consider, the seminar on Ulysses like a waste of time.
Really? Ulysses, not a waste of time.
The highlight. No.
All right. Fun. I can't do fiction anymore, man. It's rough. I don't know what's happened. So, Thomas, all right, let's talk about some science. Here is my abridged historical account of attitudes towards fMRI in neuroscience. This is roughly chronological.
Yeah.
It's great. It sucks. Oh, hey, it's great. It sucks. And then kind of maybe back and forth a few more times. So
yeah.
I don't know if that's accurate to you, but when fMRI was introduced, from my understanding of the history, it actually took a few years for people to figure out how to use it properly, how to use it well for experiments. And maybe one of the first useful ways of doing this that came along was the subtraction method, where you subtract the activation while someone is looking at a tree, for instance, from the background activation when someone's not looking at the tree, right?
Mm-hmm.
And then there have been multiple advances along the way, which I'll just skip over, and then comes along this new shiny object, which is multivoxel pattern analysis.
Mm-hmm.
And in fact, when I started my postdoc, there was one of the selling points to me was like, oh, here, I don't know if I should name the name. It's Frank Tong. It was like down the hallway. And it was like, oh, he does multivoxel pattern analysis. And that was like a selling point. Oh, that's the new way to go. What is that? What is multivoxel pattern analysis? And what's good about it?
Well, hold on. I just want to say that my general feeling about fMRI, given this cycle of enthusiasm, is that we still, as a community, are not doing justice to the quality of the data.
Oh, I see.
The entire brain, and given the amount of coverage, the resolution is actually excellent. Pretty reasonably well resolved, given the fact that you're seeing the entire brain in depth.
Yeah, shouldn't we have it all figured out by now?
I mean, it holds out the opportunity of figuring out a lot more than we have, and I think that we're still trying to figure out how to analyze this insanely rich data, right? So fMRI started out as big data, and the techniques and the ideas to analyze it they weren't there, and people did, I think, brilliant things simplifying the data down to in a way that allowed them to make incredibly important discoveries in the kind of the brain mapping era, the kind of what does what, or what might do what era.
I remember I had a tiny bit of training. I did a rotation in graduate school, and it was an fMRI lab. And I remember literally in Excel, like an ROI, a region of interest, adjusting a circle on a picture of a brain, and then using the data, like counting the data in the circle. I was like, well, this is crazy, but it's a simplification.
It is. And, and choices were made, and you're right. I mean, as a field, I shouldn't say we, because I came to it rather late. People have been constantly refining their approach. Okay, so you kind of go up through the kind of subtraction era and into the MVPA era. And what is MVPA? It's a way of trying to extract information from patterns of brain activity patterns. I mean, the best way I can think about it, or to kind of summarize it, is take any number of n voxels and you can think of it as a vector. And up until MVPA, people were just analyzing the length of the vector. Mm-hmm. And they didn't really think about what direction it was pointing in. And MVPA gives you a set of tools for deciding if two vectors are pointing in a different direction, a significantly different direction. Mm-hmm. Right? So that's a simple, right? So if the two vectors correspond to seeing a face, seeing a place, or to thinking about something versus seeing something, you can start gaining a lot of information. Instead of, what does what, you can start saying which states are discriminable from other states. That's a much more detailed query that you can make if just by taking into consideration the orientation.
So you can decode a lot more.
You can. I mean, it allows you to do decoding, right? Because, I mean, you can divide the space of brain states and you can put them into two buckets and you can say, all right, now I've measured a brain state. Is it in bucket 1 or bucket 2?
Right.
And then, yeah, you have a decoder. I think, right, so the thing that is missing, which is kind of obvious now, I hope, is that, all right, so you have two vectors and they're pointing in a different direction. Why? What do they actually represent?
Right, right.
And to answer that question, you have to build a model that transforms, in my case, in the case of vision, stimuli into this vector. And that transformation, understanding and building, designing that transformation takes a lot of work. And that's kind of where I think that's where the field is right now.
So one could say that one of the things that MVPA is missing in that sense is representation.
Yeah.
So the term representation can be thorny, right? It's been referred to as a filler term, for instance, and that it gets used like when we don't understand, how something works. We can just say that something in the environment is simply represented by the neural activity.
Right.
And in the case of like MVPA, that would be like the pattern of voxel activity. And then there's an exhausting philosophical thread, speaking of philosophy, as philosophical threads tend to be exhausting, that on what would even count as representation. And you can go down that hole and never come out the other end, of course.
Yes.
So representation plays a central role in your approach to brain processing with these models. How should we understand representation in the way that you use it?
Yeah, I think it's a fine word. I think, I mean, it can be used meaningfully, I think. So when I use it, I typically mean something very specific, that there is an encoding model.
So it's defined by the fact of there being an encoding model?
Yes.
Gotcha.
That is what I mean when I use the word representation, I mean, I'm referring to what is being encoded in brain activity. And there are tests for determining what is being encoded, or at least for adjudicating between different hypotheses about what is being encoded. And you can argue what the best way to test or to adjudicate is. Mm-hmm. I think there's plenty of reasonable ways to do it right now. But the idea is that what you want to know, so again, this is very vision specific, is, brain activity has a nonlinear relationship with stimuli, visual stimuli. Okay? And how do you conceive of that nonlinear relationship? The approach I've been taking is, and many others, is you think of the stimulus in its rawest form, a pixel-like representation of the stimulus being transformed through a nonlinear operation into a feature space, and defining that feature space, its function, its properties, whether or not it's efficient or optimal. It's a really interesting set of questions where my mind is sort of parked and has been for a long time. And then the whole process of building encoding models is really an exercise in testing whether this feature space that you've defined is going to predict variation in brain activity in the parts of the brain that you find interesting. Mm-hmm. But it's in defining the features and in the representation that I think the real interest lies for me. It also is a gateway into, I think, questions not just about representation, but about processing, which is another vague, another word that sort of means everything and nothing simultaneously.
But processing has sort of taken over in my mind as the important thing.
So my working definition of it, I agree, it is the important thing. My working definition of it right now is you want a model that's flexible enough to be queried in multiple ways, that can tell you about multiple, let's say, operating modes of the system or of the subject. All right. So again, I'll just refer to my own work because these are the examples I'm most familiar with. You can look at a picture, you can imagine a picture, you can attend a picture, you can detect a picture. The same cortical machinery is being used in every one of these cases.
Mm-hmm.
The tasks I've just referred to have, very different criteria for success, but the machinery that accomplishes them, we know, is the same. Right? You're getting engagement of visual cortex broadly construed with every single one of those things. So defining an architecture that can predict brain activity states in these different operating modes, right? Either by and not by just sort of pulling one model out and putting another model in.
Yeah.
But a model or a way of relating brain activity to cognitive state and to stimuli that, by reconfiguring its inputs or adjusting some smallish set of knobs, right?
Yeah.
We can explain how the brain transitions from these very different tasks.
Yeah.
That's what processing means to me, and I think that's where I'm trying to head, and I think that's where the field needs to head, in my opinion.
Yeah. So, okay. Well, maybe in a really broad sense, let's just go through. I mean, do you call it Voxelwise modeling these days?
Oh yeah. I mean, the Voxelwise is helpful to people working in fMRI because it distinguishes the approach from MDPA or ROI centric, but it could just as easily be cell-wise. I started off talking about how the same computational model applies to very different measurement modalities. So models that were built, trying to predict single neuron spiking activity, transported just effortlessly to bold activity in voxels. And now I have, I have 2 photon activity that a colleague has given me, or 2 photon images, right? And I can just sort of apply the same model to predicting signal change in individual pixels, right? So these are small pieces of cell, and they work.
Once you get it into a feature space.
Yes, right.
So okay,
right.
well, but the basic thing is you take an image, let's say, or some stimulus like an image, and then you build an encoding model to take that stimulus and transform it into a predicted brain activity for whatever kind of signal that you're measuring.
Yeah. Right.
And then you can actually build a decoding model based on the encoding model and the activity, and decode out the stimulus from the brain activity at that point. And so you have a kind of a full circle system.
Yeah. So there's, right. So if all you want to do is decode, you can skip the encoding step if you want to, but there are advantages, scientific and technical, to building an encoding model first. Well,
it's explanatory, right?
Yes.
Okay.
If you want to explain brain activity, you need an encoding model, right? So, I mean, here's an example that I discuss a lot, or sort of just a thought experiment. There's basically an infinite number of things you can read out from a brain area, and some of them are really trivial, right? So I could give me any, 50 voxels from any brain area, and I can read out really dumb things like whether or not there's an image on the screen, just like luminance or contrast. It counts for a huge amount of variance, right?
Yeah, that's true.
So I can decode that with 100% accuracy from some mysterious visual cortical area deep in the ventral stream.
You don't need AI to do that.
Right. But it obviously doesn't mean that that's what this interesting ventral stream area does. It's just, I mean,
we learned the light must be on, guys. That's what we learned.
Right.
But, yeah.
So you can really you have to be careful with what you infer from decoding success. An encoding model, on the other hand, would reveal, if you built an encoding model in which contrast was your only predictor and you're deep in the visual cortex, it is going to account for a lot of the variance, but not the variance that makes it interestingly different from previous or the next visual area, the one that we're actually interested in, the one that discriminates certain kinds of objects from another. So encoding models let you know how far you have to go before you can claim, well, they define victory and they give you a measure of how far you have to go to be able to claim it. Now, that measures prediction accuracy, and there is a difference, I think, between accurate prediction and understanding. Another philosophical issue, an important one, but encoding models have that that very strong and particular advantage of letting you know where you stand.
So let's maybe talk about them using an example from your work. So one area of study that you pursue is mental imagery, which you've already talked about, which is yet another fun philosophical deep dive that one may never recover from. But
I mean, the cool thing is that I really do think that progress can and is being made on mental imagery, which is this thousands of year old question,
philosophical question, and science is helping make progress. Yeah,
really, which is really gratifying. That's, as I mentioned earlier, that is the exact reason I got into science, is to pursue these kind of philosophical questions. So you can make a lot of progress using techniques that have been built to study visual responses. So the thing we've been working on for a while is imagery encoding models. Mm-hmm. So these are models that relate brain activity during imagery to stimuli that you've asked subjects to imagine.
So you see a Van Gogh painting, and then later you're asked to imagine the Van Gogh painting or something.
Yes. So what features of that stimulus that's being imagined now, not seen, are encoded in brain activity? How is that code different from the code you would get if you were seeing it? Okay, so questions about, are mental images really images? These old philosophical questions.
Yeah.
They sort of evaporate. They're just sort of like fog that blows away. And you pose these concrete questions. Here is brain activity, measurable brain activity, and I can build a transform between stimulus and brain activity. And I can do it when people have sat there looking for hours at an empty screen, and just a mostly empty screen, looking at tiny little cues that says, imagine this, now imagine that, now imagine that. I can build maps between unseen stimuli and brain activity that are extraordinarily, in my opinion, I think they're really remarkably accurate in terms of their prediction power. You can predict what people are, how people's brains are going to respond when they're imagining hundreds of mental images. Then there's concrete questions you can ask. They're not philosophical. What is the peak of this the tuning curve for imagined versus seen spatial frequencies? Mm-hmm. What is the region of imagined versus seen space that most excites a voxel? How large is that region? Does it move between imagery and vision? These are really direct questions that you can answer. So you can kind of make these measurements. Well, I'm saying you can because we've done it. And it was a question whether or not you can apply these methods, to me at least, whether or not you could apply these methods and have them tell you anything meaningful. By these methods, I mean visual encoding model methods to mental imagery. There's then a challenge, and you do see very, very real differences, it seems, between how seen and mental images are represented. Perhaps not surprisingly, the code for mental imagery is less specific. And I think that accords very well with most people's experience of mental imagery.
And intuition, yeah.
And intuition. But to be able to measure it in terms of receptive field size and spatial frequency tuning function is very satisfying. I mean, it really removes the debate from the kind of discussion about mental imagery out of the realm of philosophy and kind of internal thought experiments. But then you have the challenge of explaining what kind of computational framework or what kind of network architecture will produce these different codes, these distinct brain activity codes.
I suppose this is where your sort of theory of mental imagery comes in. It has to do with predictive coding. Do you want to talk about it?
Yeah, I would love to. So this is an example, I think, where developments in AI have been essential. Right. So there's a theory of generative modeling. It's been around for a while. It actually predates deep learning by many years. But it provides such an obvious and tantalizing framework for thinking about mental imagery, because one of the things that distinguishes generative models is the ability to synthesize images. And it's something. So if you conceive of a generative model as being implemented in a network, it will be a network that has connections that map not just from stimulus to internal state, but from internal state to stimulus.
Mm-hmm.
And you can clamp internal states and propagate activity back toward the sensory layer and get a picture.
So what does that mean to clamp an internal state?
Clamping. So formally, in our model, clamping is conditional inference. So the theory, and this is not my theory, this is a theory that others have worked out and explored for many years prior to me, my work on mental imagery, is that the visual system somehow represents a distribution, a probability distribution over representations of things in the world.
Mm-hmm.
This distribution can tell you how likely it is for certain sets of states to co-occur, right? Sky and blue, beach and sand, whatever level of representation you might be interested in. Now, in that context, vision is cast as posterior inference, okay? So you want to derive a distribution over a set of visual features given the stimulus. So the stimulus is taken as a given, and it kind of makes sense, that there are no feedback projections to the retina that can kind of, by which you can cortically control retinal activity.
Right.
So in some sense, it is taken as a given. Now, you can extend that notion. What we've done is just kind of extend that idea to account for mental imagery. So we make the assumption that the kind of clamping that takes place in the retina can happen internally, right? And this is a representation level assumption. I don't have a theory about how this happens physiologically. Yeah, but the idea is, so you can sort of treat as certain an internal representation, like a dog is out there, right? And then you can run inference again, right? So you can infer what are the most likely set of features given whatever the retina is showing me right now, and this internal representation, this clamped state that we're treating as knowledge, we're treating as certain,
as the stimulus.
Yeah, you're effectively treating it. You're kind of elevating it, giving it the status of a retinal stimulus. Mm-hmm. Very intuitive, right? All this, this probabilistic stuff, though, gives you a framework for making that intuitive idea formal and then producing predictions about, right? So if you equate, or let's say you analogize these internal states that the generative model describes with brain activity, you can easily, in a fairly straightforward way, get a prediction of what is going to happen in the brain when this high-level state is or is not clamped. And then you can also play games where you can kind of manipulate the coherence between what is being seen at the retina and what is being clamped internally. Right? So mental imagery, in our model, mental imagery is what happens when the retina becomes uninformative. So it remains fixed, and it's simplest if you just treat it as a blank screen, while the clamp states vary. Right? So you're varying your mental image, but the screen is staying fixed.
So all pixel values have the same value, or it's like a field of noise or something?
Right now, so I think the important thing is that the stimulus remains fixed while the mental images vary.
So it's uninformative. Either way, sorry, it's a technical.
Yeah. But mathematically and experimentally, your life is made easier if you just treat them as being turned off.
I see. Yep.
Yeah. There's a bias term that you don't have to carry around anymore.
Which makes sense.
Yeah. Right. So then the question is, what happens when you're driving the brain from above instead of below? That's the simplest way to put it. And there's some really basic properties of vision come into play. Okay, so one of the things we know develops in the feature spaces that the visual cortex represents across its hierarchy is invariance. In order for some cluster of cells to be able to identify an object whenever and however it's presented, it has to be invariant to a lot of its details. Mm-hmm. Okay, so if that now is your source, if that neuron is kind of your source, those cluster of neurons are your source of input for this imagery process, okay? And you tell a subject, imagine a cat over here, imagine a cat over there, imagine a cat that's gray and that's blue. Those neurons their activity might not vary much. So that lack of specificity is somehow, it makes sense that you might expect it is going to be sort of propagated back down the visual cortex and homogenize the activity, right? And you're going to get a loss of specificity, and it's going to make lower level visual areas during imagery look a lot like higher level visual areas do during vision. So these are all intuitive. You can implement them using the kind of the framework of generative modeling. You get specific predictions, and it works. It pans out. At least in our experiments, right? You see, in terms of the features, the selectivity that we've looked at, which is very simple, just spatial frequency tuning for seen and imagined features, and seen and imagined receptive fields. V1 imagery receptive fields and spatial frequency tuning functions look a lot more like they do during vision in higher level brain areas.
Without the sort of bottom up stimulus driving activity.
Yes.
So is mental imagery then, back to the predictive coding aspect of it, is it a form of predictive coding? Is it separate?
What I am saying and thinking is it's inference.
Okay? It's inference.
Yeah. So vision is inference. Mental imagery is inference. In a formal sense, the only thing different is the conditioning set. During vision, you condition on stimuli. During mental imagery, you condition on stimulus and some clamped internal state. In both cases, if you want to conceive of inference as being implemented by a network with feed-forward and feedback connections, the activity is flowing along those same connections, being integrated at every point by the same rules. Now, that's where you maybe want to start thinking about predictive coding. Predictive coding, my understanding of it at least, is it's a way of implementing inference in a network. If you go back and look at the Rao and Ballard paper that, to my knowledge, introduced at least the term, and really it's very influential, I think, in terms of getting people to think about predictive coding. It's formulated as the same kind of model that we're using right now to make our predictions about mental imagery. It's a latent Gaussian model. It's a stack of Gaussian variables. Mm-hmm. Now, how you run inference with that generative model, I think, determines whether or not you have predictive coding on your hands.
I see.
Okay, so the way they did it is to take gradients with respect to state. So they kind of cast the inference problem as one of finding equilibrium in a dynamical system. I think it's a perfectly valid and fruitful and informative way to think about it. Something that's associated with predictive coding is a very kind of specific assumption about the propagation of prediction errors. Prediction errors being propagated forward, predictions being propagated back. You can set up a neural network that implements things in that way, that implements inference in that way. I don't think it's essential, though. So I would see that inference, probabilistic inference as an umbrella, and predictive coding as particularly intuitive kind of point underneath that umbrella of operations.
So is this is this a principle, this imagery type inference, is this a principle that extends to all cognition or just perception?
We're pursuing that idea.
Oh.
Okay, so what we presented at CCNLS just a few months ago was some modeling work suggesting that you can account for a number of phenomena you see in the attention literature using the same idea, the idea of clamping and inference, conditional inference. So in this approach, what distinguishes imagery from attention is that during attention, you actually turn the stimulus back on. Uh-huh. And then you get this rich set the stimulus does vary, and the clamp state can vary as well. And you get this rich set of interactions that can drive spatial frequency tuning functions and receptive fields all over the place. you can see really dramatic changes in the way that the intermediate areas are representing stimuli depending on how you kind of tune the representation in the clamp layer and its relationship to the stimulus. So I think there's some generality there. And that actually segues nicely into the natural scenes project. For my grand designs, right? So if any of this stuff is true, it should be able to scale, right? Or whatever is true about it should be able to scale. So what does that mean? So that means that, right, in order to account for mental imagery, I'm making really pretty strong assumptions about what the visual cortex can do. I'm ascribing operations to it to account for mental imagery. And if any of that is true, then I should be able to, it should give me a more accurate predictive model of brain activity in any state, right? Including just kind of passive vision. So my idea is, or my aspiration rather, is to enter a stage where we can test hypotheses about network architecture. And again, I'm not taking credit for this idea. A lot of other people thinking along these lines. By inferring network architectures directly from brain activity.
So to do this, you decided to spend 7 years collecting a ton of brain activity.
Not 7 years, fortunately. Kendrick is among his many complimentary things I could say about him. He's lightning fast, and the really talented postdoc Emily Allen and grad student Yihan Wu, they have put together a data acquisition effort that is truly heroic. So
we talked about it a little bit when he was on.
I think he was just getting started when you guys talked.
He was already seemed a little overwhelmed, but yeah,
they did it. So we just completed acquisition on the core part of the experiment.
Congrats.
Just a few weeks ago. What they were able to do is so the stats are it's 8 subjects, 10,000 images seen by each subject 3 times each.
These are naturalistic images, like the one that's on your website.
They're photographs. They're pulled from a computer vision, from a database of images that the computer vision people put together. It's called COCO. The reason we chose it is because it's richly annotated. It also kind of narrows the visual world a little bit to hopefully make things a little bit more manageable. So there are certain kinds of objects that show up over and over again in a variety of different locations. So it allows you to explore, hopefully, we're hoping, issues of object recognition and invariance at the sacrifice of a little bit of breadth. Some kinds of objects only show up once in this massive barrage of stimulation. There are cognitive tasks associated with it, but the idea is now you can take a bunch of data, enough data that you can kind of put it into the machine learning pipeline and start trying to test hypotheses about, this is what I'm interested in, about how the whole system, the whole visual system, and all of its parts relate to one another. And cast those hypotheses as, I think the most likely candidate right now is a kind of neural network. And the space of architectures and nonlinearities you could explore is vast, but I think we have the data to do it now.
So you're going to be using your encoding model's approach throughout all the layers of the visual system? Is that?
That's what we're doing right now.
Yeah.
So now, though, you have enough data where you can do 2 things at once. You can learn the feature map. So you can learn the nonlinear map from stimulus to feature space. You can learn multiple sets of features that are compatible for different brain areas, and simultaneously learn the coupling, which is the encoding model, between those features and brain activity. And you can do it all at once. And it's working. Yeah, I mean,
it's great.
You get beautifully accurate predictions. What we learn from all of this is, that's just a starting point. That's like, it's just kind of showing we can do the thing with the data that we hoped we could do once we had it. now we're starting to dig in and consider interestingly different approaches to predicting brain activity, where the difference lies in network architecture. At least that's what we're focusing on right now.
So at the very beginning, toward the very beginning, we talked about how when you have this idea, and then you can kind of just immediately see the future, the consequences, where it's headed, like the end point. Where is that? What is that end point, and how many years? I mean, I know another feature of this is it always changes as you make progress, of course.
Right, yeah. So I'll give you my vision for this sort of far enough ahead that it's not, it's just sort of blurred out into just pure wishful thinking.
From your mental imagery, your early visual cortices right now have a very blurry image. Yeah.
So as I briefly mentioned, there are cognitive tasks associated with this acquisition. So it's not just passive observation of the stimuli. It's actually a really demanding long-term memory task because the subjects had to indicate for every single image that they saw if they'd ever seen it before. And some of them hadn't been seen in, I just paused because subjects can't know this, but we're done with collections, so I'm going to move on. Okay. So some of the images subjects have not seen for a year.
Whoa.
Yeah. And they're better at it than you might have expected. There is months long above chance memory going on. So right there, hunting for signals, memory signals, understanding how they're integrated into the visual processing and then read out into this button push. To me, a model, right? So the models that we're using to predict visual brain activity right now, many of them are not, they don't handle this kind of processing, this kind of memory-based recognition processing that's occurring in parallel with all the other visual operations like object recognition that go on when you just show someone a natural scene. I think a realistic intermediate term goal is an architecture that explains both the seeing and the remembering at the same time. That's a really exciting possibility. I think that going after that goal will push the field in interesting directions.
Maybe with that, if you have just a couple more minutes, I could ask you some, again, real broad questions.
Sure. Yeah.
So this, by the way, this is really exciting work, and I really appreciate you explaining a lot of it to me and my audience here. So
yeah, it's fun.
So does AI need neuroscience?
Yeah. I mean, I said that earlier. It's definitely, a lot of people, myself included, think of neuroscience and AI as, they're in this kind of virtuous cycle where the neuroscientists reveal principles of brain function that are operationalized by AI. They show how these ideas can be refined and scaled, which we then bring back to the brain and test them against behavior and brain activity. It's possible, right? Like if you think of that the loop is going to kind of take us, the amount of time before AI kind of loops back around to needing AI, it feels like it's going on a little bit longer.
To needing neuroscience?
Yeah. I'm sorry. Yeah. I misspoke to AI needing neuroscience, right? So I don't know when when it's going to boomerang back. And this is obviously a simplistic model because there's cyclical work happening in multiple labs right now as we speak, and I'm sure the next person you interview will give you a nice example of that. Yeah, but there is a sense. My sense is that the AI is going to go a long distance before it runs into the kind of dead end that they need neuroscientists to rescue them from.
The plateau that you mentioned before, you mean? Or because a lot of people think that the plateau is coming sooner rather than later with like the limits of deep learning are nigh. Yeah,
I guess. I mean, whatever. Everything is always 10 years away. I don't know.
Yeah, that's true.
Maybe it'll be sooner than that. But I mean, AI is having a moment. Yes, AI needs neuroscience. I think to paraphrase something David Susselow said at CCN, AI is killing it right now. That's just a fact. So that's something we should celebrate.
But he said it in the spirit of, yes, AI is killing it. Get over it and keep moving forward because what you're doing is important.
I agree with that. I absolutely agree with that. The worst thing in the world would be for a neuroscientist to just sort of sit back and read popular science accounts of how these AI systems are working. I feel like we're focusing on kind of targeted questions.
Yeah.
Right. But we have in our hands the endpoint, right? We're daily interrogating the thing that AI is trying to build toward. And that will never not be relevant. I mean, not only from a conceptual, intellectual point of view, but also obviously from just a mental health point of view, right? It doesn't matter. You can have an AI system that drives your car for you. Question's still going to remain. Someone has just gone through trauma. They can't cope with their normal life. What do we do?
Yeah.
You can never get too far away from the brain, away from people, if those kinds of questions are driving you, and they have to be driving you.
One of the worries, though, and I faced this in my own little career, and I saw it a lot too, is that you go in with this sort of big question, right? You're going to figure out consciousness or whatever, and then you realize you don't know, and then you start studying a smaller piece of it. But then you start getting like, oh, okay, into the sort of learning the technical sides of things, and that becomes interesting to you. And 3 steps further down the road, and all of a sudden you're just a technician working on the nuances of electrode impedance, right? And it's like the most fascinating thing. So I can see this being a problem with neuroscientists becoming interested in AI, and then the AI itself is the thing that becomes interesting because It's easy to make progress on. So how does that?
That's happening to grad students.
Yeah.
Nonstop, and at dinners, at conferences with other neuroscientists who are running labs and graduate programs, it's being noticed that transition from the kind of enthusiasm that inspires people to understand to want to study neuroscience to begin with, to kind of full scale conversion into enthusiasm for the technical side of AI. It's fun. I mean, building systems, and AI has developed a set of building blocks, and it's like the exact fun you get with Tinker Toys or Legos. You can snap them together to make really cool new things, and they kind of work. They tend to work.
Except first you got to get your server up and running and get over some of those.
Some people get into that too.
That's true. That's all these waypoints where people get.
I am thinking of really talented neuroscientists who got really into parallelizing computation and made that job. Yeah.
It's so tempting. But then I always have in the back of my head, keep your eyes on the larger picture. And I don't know why I feel that push to try to keep it broad, because I think people are very happy when they go down that technical road.
Yeah. I think you can make it sound a little better, at least in my mind. I make it sound a little better and think of it as craft, right? So again, the analogy to creative work to art becomes really relevant here, because the same thing happens in art. There's what you're trying to communicate, and there's your mastery of the medium.
And there's satisfaction in mastery.
There really is. There's satisfaction in craft, and become, and the way we passed on knowledge of craft to each other is very old school. It's very like artisanal, and there's something wonderfully satisfying about mastering a hard thing that can be done and doing it super well. And it's tempting to trade that in for the uncertainty that you live with all the time when you're trying to figure out your little slice of the question, how does the brain work?
So mastering uncertainty is a goal that you seem to have accomplished. Then
I am addicted to the creative cycle of science, so that the being plunged into uncertainty and the feelings of insecurity and feeling overwhelmed and futility that come when, as we said, you take your beautiful new idea and you test it against an experiment, or even just write it down in a grant. That, to me, that is part of the engine that keeps me going. It's very addictive to me.
All right, Thomas. Well, I know that your engine has been running here for a while with me. I really appreciate it. So, there's a lot more, as always, that we could have gotten to, and maybe next time. And people want to learn more, they can go to naselarislab.net. And, of course, I'll link to all this stuff in the show notes. There are specific papers that we sort of glossed over. But good luck, man. I really appreciate your time.
Thanks. It's been really fun talking to you. This is cool.
Brain Inspired is a production of me and you. You can support the show through Patreon for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.
Mayday, mayday. We've left all